So, just a reminder, the big ideas from last week were or and probability. So we had another question after we asked which of these two it was. We had another question for or, which was what? Yeah, if it's mutually exclusive or not. And mutually exclusive means that it cannot be the same, or both things at the same time. Cannot be. What was your little statement about that? Yes is no. Yeah, yes is no. So if it can be the same thing at the same time, I keep saying that wrong. If it can be both things at the same time, it is not mutually exclusive. So that's the yes, it can be, no, it's not. That's her yes is no. I think it's a good way to remember it. And then here you could say no is yes. No, it can't be both at once. Then yes, it's mutually exclusive. And then our probability was just the sum. It was okay to just add those up. Now remember that these might involve doing calculations of their own. Maybe even an and calculation in there. Remember that? Okay. And then this one had the same beginning. Just add the two together. But what did we have to do after that? No. For the not mutually exclusive, we had to subtract what? The both, yeah. Subtract the overlap, we called it, so that we don't double count stuff. And then and probability. So far we've only done one version, one equation for this. We used the concept in different ways, but only one equation. What was the question for this one? Yeah. Independent or not. And the other word, we're not going to say, excuse me, we're not going to say not independent as much as we're going to say conditional. And we might start that today. Okay, so independent was, now we're talking about and be. Oops, look what I did. I wrote and up there. And what should it have said? Or. Sorry about that. There we go. Not that you can read it, it's kind of small. So this one, remember, is just multiplying. So multiply the probabilities. Multiplying numbers less than 1 or between 0 and 1 makes them shrink. And we saw that. We saw the probabilities drop when we said and. We talked about the area model being an option for doing this, where you just take the area, which is length times width, which is A times B. It's just a visual way to do it. And we also used the tree diagram where we wrote the probabilities along the way and then just multiplied the way out. Okay? Another thing we did was saw that this can extend to C, D, E, F, G, and lots of other events. You're like, it's actually not bad. It just means multiply all of them out. So we'll see that in number 4. Conditional probability or not independent probability is more involved, so we haven't totally done that. We haven't done that really at all, actually. So let's get into it. You roll a pair of dice twice. So pair 2 times, or you could roll 4 dice, I suppose you could say that. I mean, a dice, single one, 4 times. What is the probability you will roll doubles on the first roll and then a sum greater than 8 on the second? So it's not a very good color on that background, I think. It's not really there. So probability of doubles and a sum greater than 8. Okay, is this, let's practice our question. So what's the first question? Or and. So this one is and. I highlighted that with the underline for you. Okay, now we have to ask, is it independent? So does one roll of 2 dice affect the other roll of 2 dice? That needs to be in your copy. Actually, you're back there. No, they're independent, right? No 20 on the dice. So we can just multiply, and just to save some room, we're multiplying doubles times sum greater than 8. Well, probability of doubles, if you remember, it's the diagonal in that chart, and there are 6 of them out of how many? Yeah, so this is 6 out of 36. And then sum of 8, I don't know that one, we'll have to count. Did anybody count? 10. It was 10? Okay. So 10 out of 36, we just multiply to get that number. We could simplify ahead of time. Like this becomes 1/6. So I don't know what that is, but we could simplify. Number 2, when can you use the multiplication rule for compound probability? Compound meaning more than one thing is happening. So what has to be true in order for us to use that rule? Okay, it has to be and. Perfect. So and, right? Independent. That's the big one. If it's not independent, we can't just straight multiply our probabilities. If it's not and, if it's or, what are we doing? Anyway. Are we multiplying? No, we're adding, right? So that's not an issue. Assume 63% of people chosen at random wear sneakers. What is the probability that both Colin and Imelda are wearing sneakers? How do we do that one? This is like, what's the probability that both people put ketchup right on their fries? Or versions of that? Say that again. You can use with an area model. Yeah, if you want. It would look like this. So maybe just pick one person on each side. So Colin, 63% is just over half, so maybe just there. Colin is, well, so yes is the bigger section. And 0.37, no. And then Imelda's the same, 0.37, 0.63. Okay, and then what is the probability that both of them are wearing sneakers? So which, in terms of top left, top right, bottom left, bottom right, which section are we looking at? For both of them wearing sneakers. Should be this one. Top left, because this is yes and this is no. Okay, so the area of this is 0.63 tall and 0.63 wide. So we just multiply. But it's just this, isn't it? Like A would be Colin, B would be Imelda. So probability of A times B is the area of that little section. Okay? Again, that is just a visual for that. Let me do this and then I'll say that. Why did I have a syntax error? Oh. It's because I was thinking dot. That's funny. 0.3969. Anyway, this area model is just a visual of this rule. It is not separate in any way. It just puts it down graphically, is essentially what we're doing. So probability that both of them are wearing sneakers is 0.63 times 0.63. 39.69%. Alright. Probability of flipping 4 tails in a row on a fair coin is what? Like how, I should say. Should we do that? Is this and or? This is and, right? Usually we represent it like this. You saw that in your packet on Friday. 4 tails. So what is the probability of flipping 1 tail? It's a half, right? You agree that this is just a half times itself? 4 times? So you can write the fraction version as 1/2 to the 4th. Well, 1 to the 4th is 1, 2 to the 4th is 16. So we have a 1 out of 16 chance, which is roughly 6%. 6.25%. How'd those go? Yeah, do a thumb someplace. Okay. These turned out to all be and probability. That's a good reason to review the or and keeping in mind what is mutually exclusive. How about, Braden, can you explain that again? What is mutually exclusive? Yeah, well, mutually exclusive means that they cannot be the same thing, the two things at once. Like you are a student here and a student at Career Center, right? Oh, okay. Last semester you were? Yeah. So last semester you were not mutually exclusive to either place, like you were both. Now this semester you only go here. Yeah. Okay. Well, this is kind of like what a test might look like, where it's just random questions just fired at you from different scenarios, okay? And not might, it will look like that. Some of the test questions will, like, let's say, take 4 or 5 questions from one situation and ask it just various things about it. But some of them might be completely unrelated, like these were. I had you working on 3 problems on worksheet. It's called worksheet 12.1. It's this one. No, let me get there. Why don't you grab this one, please? It was 11, 21, and 24. Yeah. I would have said Friday. I don't know if we're gonna get there. We don't have a ton left, but it depends. If you can pick it up like in a day and a half, then we could probably pull this off by Friday. And most of the next stuff is, I like it. I think it's very interesting.
You said we weren't like getting super deep into it
Because it's not a standard.
Yeah.
We're not going to do the hardest stuff. So that's good. All right. Can you look and see if, so 11, 21, 24. And then out of those 3, hold up how many you have done. 2, 3. We had time in class to work on this. It was like 20 minutes on Friday. Okay. So I think what we'll do is take, you had 2, right? Sylvana, I didn't see yours, I think. 11, 21, 24. 2, okay. Let's take like 7, 8 minutes somewhere in there to finish, and then we'll check them, and then we'll start that next stuff. See how that goes. So number 11, this math teacher wears scarves sometimes, and this, I don't know if Murphy's a boy or girl, but anyway, Murphy's documenting the relationship between that and him having a quiz. I'm going to say it. Oh, it does? Good. So, pause and think about what actually this is going to tell us. If the events are independent, is there any link between scarf and quiz? If the events are independent. No, right? Independent means no predictable pattern. If it's dependent, then there is possibly a prediction where a scarf means quiz, right? Okay. Well, right now, we're going to have a little bit more in-depth test for this. In fact, we'll even call it the test for independence. But right now, it's just going to be simple. It's actually not too far off, but we're thinking of it conceptually as a simple thing. the formula, I mean, is not really that far off. It'll just look a little different. So, when is this formula usable? When is it okay to use? This one I just wrote. When is it okay to use that formula? If it's independent, right? That is the only time we can just straight multiply, is if it's independent. So in these number 11 and 21, we're going to use that to check. Here's how. We're told the probability of having both is 5%. So I'm going to write that as 0.05. The other two numbers we're also told, so probability of scarf is 0.1 and probability of test is 0.15. If this equation is true, then this is independent. Do you remember when we used the Pythagorean theorem to check if a triangle was a right triangle? So we were given all three values, and we weren't trying to solve for anything. We were seeing if the equation was true. Do you remember that? That's this. We're just seeing if the equation is true. If so, it's independent, or at least it must be, because it's working in an independent equation. If it's not true, in other words, if these two don't equal each other, what do we conclude in that case? If the equation is false, what do we conclude? If we're using an independent probability equation and it's false, that tells us it's what? Not independent, because the equation for independence didn't work. Okay, when you multiply this right side, we get 0.015. What was it? You did it a second ago. I said it, 0.015, right? I keep writing it wrong.
0.01.
Yeah. Are those equal? So is this independent? No, because the independence equation didn't work. Okay. My son actually has a teacher last year. They figured out that if he wears black, like if he wore, I guess this guy likes to wear plaid short sleeve shirts or like a hoodie or something like that. But if the dude came in with a black, it was not going to be a good day. It's kind of what they concluded based on their analysis. So it's this, right? In both cases, it's not independent because there was a connection between what the person was wearing and what happened that day. I want to pause there and write this as a brief conclusion. Again, we're going to have a specific test that is similar, but not exactly that. And the reason why is because we're not always going to have the probability of both being given to us like this one was. So I'm putting this right after our independent equation. So here's what we're writing. If you plug all three probabilities into this equation and both sides are equal, then what's the conclusion? If the equation is true, it is independent. I gotta get you straightened out. What if it's false? Yeah, let's go ahead and write that too. This is the concept behind testing for independence. That's okay. This is not going to change. The thing is, we don't always know this one. Just we can't necessarily calculate it if we're not told it, right? So that's where we'll twist this slightly to look a little different when we're given information in a different way. But this is the concept behind it. If this equation is true, it's independent. That's really all that says. All right, 21 asks a similar question, but let's do the probability first. So we have 7 marbles, 5 are red. What's the probability of drawing 2 red marbles? When we put the marble back, that's what changes this a little bit. So probability of 2 red, is this independent? We kind of need to know part B before we do part A, don't we? Well, what does putting the marble back do? Yeah, resets it. So is it independent? If I reset, doesn't that mean independent, right? Okay. So this is probability of red times probability of red, which is 5 out of 7 times 5 out of 7, or 25 out of 49. Probability. Okay? Now, this time, this is a good example. We just wrote down how we know if it's independent, but we don't have enough information. If we were told the 25 out of 49, then we could have said yes, for sure. But since we weren't, we had to rely on the statement, if it's replaced, that makes it independent. If it wasn't replaced, not independent. Because it would change, right? If one event changes the other, not independent. How's this going so far? 2 for 2? On the second timer? Alright, 24. Kicking a field goal. So the probability that this kicker will make a field goal is 0.8. This time the probability is given as a decimal, which is fine. What is the probability he will make both field goals? Both implies which? And or? That's definitely an and, right? Make and make. Alright. Well, what's the probability of making the first one? He walks up there to kick. What's the probability he makes it? 0.8. Good. So 0.8 make. What's the probability he makes the second one? 0.8. So 0.64. Just leave it as that decimal. But the question is, I just wrote it up here as if it's independent. Is it? We're going to assume it is. I think in reality it probably would be a little bit dependent. And you probably all have the psych out effect at some point, right? If he missed 5 in a row before this, it's probably going to mess with his head. It's not like every time he's just robotically 0.8. But for the sake of this problem, it's independent. How about the next one? What's the probability that he makes neither?
Doesn't make one at 0.02.
Okay, so probability of missing is 0.2 and 0.2, so 0.04. That's what you got, right? 0.04. So a 4% chance. That would be good to know as a coach. But again, in reality, there's a lot more going on than just raw probability, right? Okay, how did that one go? Guys, if this is going badly for you, I really need you to come in and get some help, so we can kind of identify the source of the confusion and address it now. because we're not too far from the end. And of course, as we go, we're just adding more things. Please just come in at lunch or during advisory to get some help. Okay? All right, well, that concludes those two for now. And let's go look at probability. Go back. Okay. Grab those notes. So, conditional is the word that we're going to use for not independent probability. And we're not going to get super far into this, but we'll probably get a little bit of understanding. All right. At Central High School, 85% of all senior girls attended. This is worded weird, by the way. And 65% of all senior boys attended the spring dance. So 85% of girls, 65% of boys went to this dance. 20% of all attendees won a prize. So everybody hear two things. Attendance and winning. Those are kind of the two that we're looking at. Yes, there's girls and boys going on too. Okay. So let's read a question that this will sound like when we get into it. Assuming that the number of senior girls at Central High School is about equal to boys, estimate the probability that a randomly selected senior, so pick someone at random, won a prize at the dance. Do you hear kind of some increase in the complexity a little bit of this? So a little bit more complex given statement, and then our question is a little bit more involved. Do you think it's more likely? Oh, let me ask you this way. Do you think knowing the gender of the student affects knowing whether they won a prize? Based on this, does knowing the gender of the student affect knowing whether they won a prize? Do you hear me asking a dependence question, like, does it matter or not? Okay? So start thinking that way. I'm going to say, or point out, that there are more girls than there are boys. So does that change whether they won a prize or not? Or, sorry, whether we know if they did or not? Whether we expect to know that? At first you said no. It's different if we look at the fact that there's more girls than boys. Okay, we'll come back. I'll try to remember to come back and do this once we get some stuff, because it's a little vague right now. All right, so independence versus not. I think you can probably all relate to this table, so I want you to look at it before we read anything. This is a club membership table by grade. So sophomores, juniors, seniors, drama, science, art. First question. Could one person or more, could a student be involved in more than one club? Okay. Can a student be in more than one level of class? No. So some of this is overlap and some of it's not, right? Like, or can overlap. Okay. Next thing I want to point out is this row and this column are totals. So our data is really just this 3x3 table. That's our data. The rest of it is just adding stuff up. Okay? And then specifically, tell me what that number is right there. Yeah, the overall total students. And notice that you should get that total from both directions. It should be the same from the left and right and the top and bottom, okay? And if not, if you add them to the right and it doesn't add up to the same thing coming down, then it's something in your table is off. But that total should be the same both ways. So this is called a two-way frequency table. It's two ways because again, we're going horizontally to one total and vertically to the other. So it's breaking this up into categories of two types. Does everybody see the two-way part of it? Okay. And then the word frequency just means how many times is it occurring, that's all. Like how frequent is that occurring. So like a senior in drama occurs 8 times out of 17. So its frequency just means how many times does it happen. So I think you will like these. I think. Once we get some notation down and you understand how to read stuff, all the information you could ever need is in there, in that table. It's just reading it correctly. So I personally like these a lot because of that. Okay, let's read the problem now, and then I'll show you kind of how it works. We'll see what time we have. Not much. Let's try it before we go. Okay, what is the probability that a member of the art club selected at random is a junior? Okay, so I'm hearing some numbers. Okay, first of all, are these two independent? Does knowing that we're picking a junior affect how many kids that we look at for art? It affects it, right? It is not independent because in terms of art, like that's not the same category or same number, as the other two classes. They're the least. So knowing that it's a junior affects how many art students we're looking at. Not independent. Okay, let me hear your numbers. 16, what did you say?
16 out of 18.
Okay. I heard you say one.
16 out of 40.
Okay, so do you see how we have two options? Which way do we go here? Alright, that's what we're going to figure out. In this case, it is this way. So 16 out of 58. And it's because we were told that we're looking at art club. So we go this way. Okay? But I will give you a really easy way to figure that out.